paper. So, particle size distribution curve, gradation curves. The curve showing the result of sieve analysis representing the distribution of particles of different size of the soil mass on the semi-log scale is known as particle size distribution curve. So, this curve is also known as grain size distribution curve or gradation curve. Particle size diameter d is plotted as abscissa x axis on log scale, whereas percentage finer, the percentage passing through each sieve is plotted as ordinate y axis on natural scale. The semi-log scale is chosen. The plotting particles, the plotting particle size distribution curve as it gives the best representation for wide range of particles existing in the soil mass. The range of the particles varying from 80 mm to 75 micron is very large. Thus, for a better representation is required on the horizontal axis, further semi-log scale provided as shown in this figure. So, this is the plotting on the semi-log scale graph sheets about the particle percentage of passing on the y axis and grain size, particle size on the x axis. So, these are so many curves that shown in this table up to the micron levels, millimeters level, and on the right hand side on the x axis that shown 100 to 10, 1 mm, 0.1 mm, 0.01 mm, 0.001 mm means 1 micron, 0.0001, 0.1 micron. So, on the y axis, that is the percentage passing 1, 0, 10, 20, 30, 40 up to 100% passing material on each sieve. So, in the left hand side, that is very fine size particles that are shown fine grained curves. Second is uniform soil curves. Third is well graded from the fine clay size particle to the gravel size up to. In this curve, all the particle sizes are present in this soils. So, that are shown in from 0.0001 to 10 mm, 15, 20 mm. So, next is gap graded, in which some particles are missed, that is the gap graded curves, and last curve on the right hand side is a coarser grained soil that are shown from the 0.1 mm to the 20 mm, 30 mm. So, this is the coarse grained fraction which have contained the gravels, coarse and fine, sand particles, coarse, medium, fine particle up to this, that is the coarser grained fraction. Important coefficients. The following two important coefficients related to particle size distribution curves are used in soil engineering, which are quite useful to understand the nature of the soil. Number 1, coefficient of curvature. Number 2, coefficient of uniformity. So, we explain the number 1, coefficient of curvature. The coefficient which describe the general shape of the particle size distribution curve is known as coefficient of curvature. It is denoted by Cc. So, that is represent the general shape of the particle size distribution curve. So, Cc is equal to D30 the square divided by D60 multiplied D10. What is the D60? Where D60 is equal to particle size such that 60% of the soil is finer than this size, means 60% soil that have passing through to this size. So, particle size which have contained, then the 60% of soil is finer or passing than this size. So, D30 particle size such that 30% soil is finer than this size. D10 that particle size such that 10% of the soil is finer than this size. For a well grained soil, the value of coefficient of curvature lies between 1 and 3. Number 2, coefficient of uniformity. Coefficient which describe the uniformity of the soil is known as coefficient of uniformity or uniformity coefficient. It is denoted by Cu. It is given by Cu is equal to D60 by D10, where D60 particle size such that 60% of the soil is finer than this size. D10 particle size such that 10% of soil is finer than the size. Relative density. The relative density is an important index property of the cohesionless soil. Relative density is termed as the relative compactness, for example, denseness or looseness of a nature soil deposits. It is also known as density index or degree of density, that is denoted by dr or id. Relative density dr is defined as the ratio of the difference between the wide ratio of soil in its loosened state and its natural wide ratio E maximum minus E to the difference between the wide ratio in the loosened and denser state divided by E minimum minus E maximum. So, E maximum, the wide ratio in the loosened state, E minimum wide ratio in the dense state. E is the natural wide ratio of the soil deposit. So, these are the shown in the two states, loosened state and dense states. In the loosened state there are so many voids, maximum wide ratio, and in the compactness dense state there are less minimum wide ratio, minimum voids present in the soils. So, the relative density of cohesionless soil vary from 0 to 1. Case 1, when the natural state of cohesionless soil in its loosened form, means E is equal to E maximum in the loosened form. So, when this value put the value in the formula E is equal to E maximum, then from the equation 1 dr is equal to relative density is equal to 0. Second case, when natural state of cohesionless soil in its dense form, then natural void ratio that is E is equal to E minimum. So, relative density that is equal to 1. So, table that have also shown the relative density of the various types of the soils as number 1, value vary from 0 to 0.15, very loose soil, value between the relative density 0.15 to 0.35 loose. Number 3, between 0.35 to 0.65 medium dense, between 0.65 to 0.85 dense, or 5.85 to 1, that is very dense soil. Determination of relative density dr. To determine the relative density of the sand, we are to determine 3 values: E minimum, E maximum and E is the natural void ratio. So, in the first figure, in the loosened states, solid particles and the voids present maximum. In the natural state, voids is E, and dense state natural void ratio that have come is E minimum. So, the volume of that is also reduced due to denseness, compactness of the sample soil. So, determination of relative density dr, determination of first E, we know that dry density, that is a gamma d, is equal to G gamma W over 1 plus E. From this formula, we can calculate the value of E, G gamma W over gamma d minus 1, that is the dry density, and void ratio E, and G is the specific gravity of that material. So, specific gravity G can be determined by piconometer. Dry unit weight gamma d can be determined by sand replacement method or core cutter method. Unit weight of water gamma W is taken as 1 gram per cc. Second is determination of E minimum. E minimum, dry unit weight gamma d is maximum. E minimum is equal to G gamma W upon gamma d gamma maximum minus 1. Then we can calculate the value of E minimum. So, determination of relative density dr procedure: take a mold and measure its volume B, fill this mold with oven dried sand, place a surcharge weight over the top of sand surface and place the mold on the vibrating table. Vibrate the specimen mold for 8 minutes. Find the weight of compacted specimen W maximum, then we can calculate the Y gamma maximum is equal to weight per unit volume. So, minimum void ratio can be determined. So, for E maximum dry unit weight gamma d is minimum, E maximum is equal to G gamma W upon gamma minimum minus 1. So, take a mold and measure its volume, fill this mold with oven dry sample of sand passing through required sieve. The height of free fall of sand is adjusted to 25 mm. Find a weight of sand specimen W minimum, calculate the gamma, weight per unit volume, then we can calculate maximum void ratio E maximum from above formula can be determined. So, when we can calculate the 3 values E, E minimum, E maximum, then we find out the relative density of that soil. That is the behavior of cohesive soil with change in water content. Thanks. Okay.